Okay, right now, is it better? Okay, so yeah, so it's as a half, we're halfway there to completing the project. So let me just highlight the three aspects that were requested uh, by the French team. The method outline, which is mainly is mainly taken from the guides uh, that were given at the GitHub repository for the main project, which is the main steps, the preprocessing, which allows for preparation of matrix of the data into the form of matrix from which we extract the eigenvector using SVD. Then we compare the eigenvector to gene density on a given chromosome. From that, we can recognize the compartments, which then the results we save and visualize. The first preliminary results are that in some cases the high resolution and lower resolution give the same results of the same, let's say, precision, which means that they are more or less the same as the results, the example results that were given by Leopold with the data. But some of the chromosomes are more interesting because there were some differences between the resolutions. In this case, this is the chromosome 21. On the left, we have a resolution of 100 kilobases. On the right, we have a resolution of 25,000 kilobases and 25 kilobases. And when we align those graphs with the data that was provided by Leopold, we can see that on those graphs, the more intense the color is, the results are more alike, and the gray areas and the less saturated colors are the areas where the data weren't so good, so alike as the one provided by Leopold. So as we can see, the resolution of 100 kilobases was very varying from this data, and the high resolution of 25 kilobases appears as almost identical
Sorry,
with
you
the
have
data.
already passed 3 minutes, so go fast, please.
Okay, those are the preliminary results and technical details. The analysis of more the higher resolution takes a bit more time, 15 times more, and memory usage is also higher for the higher resolution, and it takes almost 10 times much more. Okay, this is all, and thank you for your attention.
Okay, thank you. Do we have one question, maybe?
Yes, maybe I have a question. How do you have in mind some ideas to improve the speed of your method to go faster?
I mean, we've already parallelized the process, and we split the jobs between different cores, between different threads, but we're still working on ideas how we can improve the whole analysis process.
Okay, so maybe we can move to the next team, which is Prague.
So should I share my screen?
Yep.
Okay. Can you see it?
Yes.
Right. So I'm gonna go right into the methodology because we don't have much time. So what we did, we took the pre-processing from Shrek 3D to generate the distance matrix with some minor alterations if something didn't work. And so then we did the required normalizations. We computed our color relation and eigenvalues and eigenvectors. And then we fit the Gaussian HMM Hydraean Markov model for each compartment count that was required, so 2 to 20. Where the number of states corresponds to the number of compartments. And then we took the prediction vector and we did our evaluation, which is a function that takes eigenpoints for each, let's say, cluster or each predicted compartment, and computes convex hull in this high dimensional space. And then we sum the perimeters, or whatever we should call it, of the different clusters, and the lower the resulting sum is, the better we say that our clustering is, because when the perimeter sum is low, it means the clusters are more dense than when it's high. And from this score, we choose quote unquote optimal compartment number for each chromosome. As to our results, most chromosomes would give us 2 compartments as the optimal number, which is slightly unexpected. We expected more, to get like 5 most of the time, but in some cases we got more, as you can see here. And for example, chromosome 9 there was 3 compartments considered as optimal, and in chromosome X it was 5. And this seems like it might not be entirely correct, because chromosome 2 gave us even 10, which is just, from everything from our research, doesn't seem right. But what is worth noting is that the scores quite often differ only very slightly. So this is something to look into further. We had some problems that we solved. What we didn't solve, or like we would like to compare with some more advanced methods, which managed to find one, which is quite a new article from Nature, where they use deep learning to predict the subcompartments from Hi-C data. So if we manage to get this method working, we could compare our model to this more advanced one. And so that's something we would like to do. And also maybe it would be worth looking into some other scoring method, just to have like more confidence in our conclusions. I think that's about it. Also, I just quickly...
Sorry, have already passed 3 minutes.
Okay. I just wanted to mention that we also tried k-means clustering as a substitute for IgMM, and in lower compartment counts, it is pretty much identical. When we increase the compartments counts, it diverges, but only slightly. So it's very comparable, actually. That's it.
Okay, thank you.
Thank you for your attention. Yeah.
So you say that the scores are quite close. What does it mean? It means that between 2 or 3 compartments, you have about the same score. You can't really be, there is no big gap between the...
It depends on the chromosome. It's different for each. Like it's not, which I think is quite expected, that it's not going to be same. But yeah, it is chromosome dependent. So I can tell you what the difference is if you tell me what chromosome should I look at.
I have a question.
Yes.
Not so naive. Have you detected a difference for chromosome with pericentromere, which is at the beginning of the chromosome, and chromosome with the centromere in the middle?
Oh, sorry, could you please repeat it? I didn't really understand.
Do you find a link between your optimal number of compartments and the position of the centromere for all chromosomes?
Well, I'll be completely honest, we didn't look into it too much yet.
Okay. Keep it in mind, maybe.
Yeah,
maybe.
yeah. That's definitely. Also, there's the. Can I have a question? Maybe. Is it like would it be preferable just to give one compartment number that is optimal for all chromosomes, or is it maybe better to like say this like 5 compartments is optimal for chromosome 2, but for chromosome 19 there's 6?
I like the fact that you think that there is not optimal chromosome compartment number for each chromosome. So for me, if you find some result on that direction, continue to go on it.
Okay. All right.
Okay, maybe we can move now to Heidelberg team.
Yes. Okay. Can you see my presentation?
Yes.
Okay. So, hello everyone. This is the compartment prediction team from Heidelberg, and we are Dorothee, Teresa, Elias, and me. And as everybody, we started from the filtered and normalized Hi-C matrix, and then we chose 2 ways for the compartment prediction, hidden Markov model and a method called line, which is a graph embedding. And for the hidden Markov model, we applied a PCA, got the eigenvectors, and based on the eigenvectors, we computed a different number of compartments, 2 to 9. And with the line graph embedding, we first need to draw an Hi-C interaction graph. This looks like this. You have bin 1 and bin 2, and then the interaction score. And based on this, yeah.
Sorry.
Okay. Based on the interaction score, you draw an interaction graph, and then you apply the graph embedding, and you get the low-dimensional vector space where you can apply k-means clustering, which gives you also the compartments. And so far, we have results like these. This is for the GM12878 cell line at 25 kb resolution. And this is both the same UMAP on the low-dimensional vector space of line, but colored by either the k-means clustering and the hidden Markov model states. And you can see they are at some point similar, but also differ in other regions. So this is definitely a part to compare, not only to Leopold's results, but also between our methods. And we validated our states of this from hidden Markov model with 9 states, and we validated them with the epigenetic state distribution. And you can see that there are 4 active states and 5 repressed. The blue one is, or the blue colors are all active epigenetic states, and red ones are repressed epigenetic states, and therefore we have 4 active and 5 inactive states. And this one is for all chromosomes in, again, the GM cell line at 25 kb resolution based on the principal component 1. With our analysis with some technical challenges or problems, one is the computational resource limitation, especially for line calculation, because this needs a lot of memory. And also interchromosomal data is very important for line calculation if you want to calculate for the whole genome. And there is the 25 kb resolution interchromosomal data is missing. So this is currently not possible to calculate over the whole genome. And also it's very memory intensive. And sometimes we don't know completely when, but sometimes we get these worm-like UMAPs, which is not what we want to. So we have to work on this as well. And then
sorry, you have already passed 3 minutes.
Yeah, this is the last point. This just to show which output format we want to give. So the chromosome and the bins, and then which compartment, and that's it. Do you have questions?
I have a question. Why did you decide to stop at a maximum of 9 compartments?
Yeah, you can also go further. We read 5 and 9 compartments in different papers, so we started with these 2 to 9 compartments. But of course, you can go further with more compartments.
Okay.
Could you please eventually share the 9 compartment paper, because I haven't come across that actually.
Okay, I need to look this up. I'm not sure.
Okay, thank you.
Yeah.
Just send it to main maybe later on Discord or something. Thank you.
I have a question. Sorry.
Wait, I think it's this paper where they applied the line graph embedding. They mentioned that 9 compartments are best, but then continued also with 5 compartments. I'm not sure about why exactly, but this paper.
Well, from what I understand, the 5 compartments was mostly a conclusion made from the HMM, and then these newer machine learning methods are trying to be better, I guess. So.
Okay. Yeah. Okay, but this is the paper. I can send
yeah,
it.
Thank you.
If you want to.
Actually, actually, that I know this one. Oh, thank you.
Okay.
I have a question exactly in this slide. So why k-means? Why don't apply a graph clustering algorithm?
This was just the method they used in the paper, and this works pretty well. But of course, you can also apply other clustering algorithms. There's no limitation.
Okay, so you have used this part of the code is already done. It's not you.
No, we coded this, so we just use these methods, but it's exchangeable, of course.
Okay, thank you.
Okay, thank you. So next one is Sorbonne University team.
Yes. Can you see it?
Yep.
Okay. So today, Lisa, Perrine, Quentin, Rémi, and I will introduce to you briefly what we achieved so far, how we did it, and what we still have to do. So here is our methods. We applied the pipeline and used some code given by Leopold during the kickoff meeting. For example, we used the SCN normalization of the profile matrix. And we special mention for the none and infinite values that we replaced by zeros to that was corresponding to the loss of information, or for example, a lack of signal. We computed the eigenvectors to be able to sort the first component and to make the compartmentalization of A and B. Here is some kind of preliminary results that we got for the chromosome 19 at 25 kbs. On the left, we have the correlation matrix, and we tried to perform some kind of matrix comparing it to the gold standard. So we looked at the bins that were filtered in our results and in the gold standard. And we can see that the filtering is not that bad, but the allocation of the beans gave us a precision of 52%. Here is an example of the chromosome 19 at 25 kb, a representation on PyMo. The blue color is representing the B compartment, and the red one, the A compartment. So what we wanted to implement is the subcompartment identifier that have been already described in the two last presentations. We want to implement it to be able to define subcompartments from the two that we already have and compare it to the Raoul et al. Paper that was presented during the kickoff meeting. And we still have to increase the accuracy that is about 52% that I showed previously. So that's it for the moment. Thank you for your attention.
Thank you very much. Other questions?
So maybe I have a question. So if you get this 52% accuracy, so did you actually correlate with gene density? Does this kind of compartmentalization correlate with gene density well, or? Hello, can you hear me?
Actually, we didn't try that yet, and we still have to work on this. It's a possibility for later.
Okay, thanks.
Okay, thanks. So maybe we can move on with the TAT teams now. The first one should be Heidelberg, team number 1.
Okay, can you see my screen?
Yes, we do.
Wonderful. Okay, welcome to TAT prediction team from Heidelberg. Our strategy was to design an algorithm with very high true positive rate, which in turn, of course, leads to a high true false positive rate, which we want to compensate using a scoring mechanism which implements further biological data. The algorithm we implemented was RGMap in Python, so we coded the whole thing in Python, which is originally in R, and it's based on Gaussian Mitchell modeling and proportion testing, and uses VGMM-based matrix binarization, going from a count matrix to a state matrix, and then identifies the boundary candidates using the proportion test between up downstream window and the between window, and then calls the TATs based on their bias at each boundary or peak called before. We then further adapted that to our strategy by testing it on a simulated data set with available ground truth, and used that to optimize our parameters of the algorithm. And we also implemented an iteration with different parameters because initially we detected too few TATs, and that solved it, and also averaged out the TAT size detected. And that led to a whole of 1,036 TATs detected for chromosome 1 of the Silent GM 12878, and that we further filtered with our TAT scoring. We integrated further additional biological information, mainly ChIP-seq, like CTCF, RAD21, SMC3, and ZNF143, and discarded overlapping TATs, like you can see in the middle of the image. And also we took the linearity distribution with, in a TAT into account, and that led to a reduction of detected TATs to 500 biological relevant TATs. The problems we are having at the moment is the filtering accuracy of the scoring function, which we try to solve with integrating additional information. That leads to the further problem of annotating ChIP-seq data and methylation data, because the resolution of our Hi-C data is quite low at 25 kb, and ChIP-seq and methylation data is normally resoluted at 1 or 2 kilobases. So we have problems annotating certain ChIP-seq peeps to a TET boundary, which is 25 or within 25 kbs. And lastly, our confidence in the final TETs we have to assess, because, for example, Arrowhead has a quite different distribution of TET sizes and TET predictions compared to our algorithm. And there we have to further dig into gene density, etc., to validate our results. Yeah, thank you.
Thank you very much. Very nice drawings. So I didn't understand, what do you do when you have overlapping TEDs?
We try to discard them. So, for example, we have subTEDs detecting, and due to the iteration on the algorithm we implemented, we have TEDs that have overlapping boundaries. So, like you can see in the middle, can you see my mouse? Or,
yeah.
Okay, like those two are overlapping, so it's biologically very improbable that those two TEDs are real TEDs. So we try to keep the one with a higher score regarding the other biological information we implemented and used, and thereby filtering out the bad ones.
Okay, thank you. Another question, maybe? Okay, so if there are no other questions, we can move to the team 3 from Sorbonne University. If team 3 is here. Yes. We see your screen, but we don't hear anything.
Okay, sorry, I didn't on my micro. So first, so this is our task. Our challenge is TAD, and this is I think it's my team. Yeah, this is my team. So basically, we have for now we only have 3. So first, we are representing the Arrowhead. So in the beginning, we run it's so long time, and I think it will be run more than 2 weeks for the whole data set, 100 KB. Now, and then we just move to on the next step with development the algorithm. This algorithm we just inspired by Arrowhead, and we change the design. So it's running. It's running will be finished in 5 minutes on the 2 data set. And in fact, we have another method in my mind. Maybe will be more long than first one, and it could be will be high quality for TED. So all the programs we running on the IFB core cluster server with multiple processes, even the Arrowhead. Now this is for the first method time for the 2 data set. It's for the 100 for the resolution 100 KB. It's really quick. Maybe we can verify if you like during the time question. Here now we have results. So we have proposed how to calculate the TAD score. So basically it's just calculate the error, intersection and union. For the detail how to calculate, I write a PDF in my GitLab. You can read it. So this is the score combined with the file of was given by Arrowhead domain. It's very similar, and I think my method in logically will be better than Arrowhead. So I'm not sure. Because in that time, I didn't have time to finish compare with the second data set. Because second data set, we found lots of TED, so will be take a long time. Yeah, and as I said yesterday, the server was latency, so maybe I can show you next time. So in future works, I will try to implement the second method that will be a little complicated, and then we will calculate the score evaluation. Maybe will be a new evaluation casting that proposed. I'm not sure. In the end, we will write the report will be a little long. Okay, that's all, I think.
Okay, thank you very much. Do we have questions?
Maybe I missed it, but how exactly is your algorithm working?
It's a different. Sorry, I didn't write my algorithm detail. The algorithm for the Arrowhead, we just change the window and check one piece by one piece. And now this algorithm is just the index. We use the data, and we directly fix the data. We track the position should be there. If there have some data, which means this is a TAD. There have no related data, so this is not a TAD. In the detail, I would like to write in report, because if a presentation here will be take a lot of time, I think 3 minutes, so I didn't write too much detail here. If you want,
you implemented a similar idea to Arrowhead, but in a different way. Well,
yeah, I changed the design. Actually, if compare the result, it's not the similar. It's could be different, but inspired by Arrowhead.
Okay.
Okay. If you like, I can check now, because I think there's just only one people are using the server. If you don't want.
Okay, so maybe we can move to the next presentation. So this is team 4 from Heidelberg.
All right. Just a second. Can you see my screen?
Not yet.
Yes.
Yes.
Okay, perfect. Yeah, we are Tristan, Ann-Sophie, Fabian, and I from Heidelberg, and we used deep neural network approach basically to detect TADs, and we want to present you TADNet today. The entire idea is based on UNet, which is an image segmentation network, so a convolutional neural network which is used for image segmentation, and we modified it accordingly so that we can basically predict TADs. So the biggest problem with the Hi-C data is memory constraints, and then we don't have enough chromosomes for training this correctly. That's why we created patches and split the heat map or these heat maps into smaller patches and used them then for prediction. We then reconstructed the entire map after we passed it through the network and can then reconstruct the TAD prediction for entire chromosome. And after this, we do Harris corner detections to call the corners and get our final output in a similar form to Arrowhead. The prediction is pretty fast, and as you can see here, our preliminary results. I show you the results for the cell line IMR90. And we compare always here against Arrowhead. And in this graph, you can see the Hi-C data at the top. Then you can see our called TADs compared to the TADs by Arrowhead. And then you can see how they correlate with different transcription factors here. And as you can see, ours compare pretty well to with CTCF and SMC3 and RED21. On the right, you can see what we used for evaluation of our algorithm, where we looked at the CTCF enrichment at the boundaries. And you can see that we reach pretty similar score to the Arrowhead algorithm. The difference is that that we do also super resolution from the 25 KB dataset. So we go up to 5 KB, so we can basically predict with a 5 KB confidence if where our boundary lies, because that's because the Arrowhead data was at higher resolution, and so we could train at higher resolution than the Hi-C map that was given. And down here you can see the called TEDs by both algorithms, and you can see we'll call also more TEDs with a similar quality. Technical challenges for us or constraints are that this is a supervised approach, so we always need some other algorithm as ground truth, which it was in this case Arrowhead, and of course this is not a real ground truth because there's no clear definition what TUD is. Then the training of this network needs, of course, for the training a lot of resources, and that's why memory management is key, and that's why we did a lot of optimization so that this that we can train this network efficiently. And then a drawback also is that the prediction on the CPU, although it's easily doable on a normal computer, takes a lot longer than if you use a machine that has GPU. So you can see on the CPU, the convolutions take 2 minutes, or the entire workflow takes 2 minutes, and on a GPU, it takes 2 minutes versus 20 minutes on the CPU for one chromosome. And then, of course, the corner detection, the Harris corner detection could lead to another is another error source that could introduce errors, but still our results show that we are quite similar to the Arrowhead performance. Questions?
Okay, thank you very much.
I have a question. You trained your algorithm with the Arrowhead ground truth, and then you say that it's close. The algorithm gives close result to the Arrowhead, but isn't it obvious?
All of this data here, yeah, it is obvious in the key that we replicate Arrowhead, but we are still looking here at valid data sets. So data that our network hasn't seen before in training. So if you would have done an overfit, I could show you a really great performance on the training set, but then the performance would be terrible on the validate set. So this shows that the algorithm learned to behave similar to Arrowhead. And the key, what we have, or what is really important, I would say, is that we can work with worse data than Arrowhead. Because these Arrowhead calls, they weren't made at 25 KB.
Okay, so you mean that by training on a specific resolution range, you are able to generalize to other resolutions?
No. We have 25 KB Hi-C data, but the Arrowhead calls that we received were at 5 KB and 10 KB, as far as I remember. But we are able to go from this 25 KB maps and make similar predictions as Arrowhead on 10 KB or 5 KB.
Okay.
Could you say some word about the topology of the network? How many layers?
Okay, you can see, sure, you can see the network basically here. This is the construction that is used for the UNet. You have always 2 convolutional layers without padding, and then you do max pooling, and you do this for 4 times. And with every layer you go down, you expand basically the channels so it works similar to autoencoders, if you know them. And if you at the bottleneck layer, you will expand back up. And the special thing about UNet is that you also have that you also take a copy of each state at each step before you do a max pooling layer. And then you concatenate this layer back at the end, and this is done because you will lose the spatial reconstruction features when you go down to the compressed state in the bottleneck, and to go back to your spatial reconstruction. You need these layers from before.
Ok, Okay, thank you. So maybe we can move to the next talk. Team 2 from Warsaw.
Okay, I'm sharing my screen. Okay, and so hello everyone, we are team from Warsaw. Let me know if you don't see my screen. Okay, so what we did, we implemented 3 TAT detection methods, that is top-down, arrowhead, and TAT3. We implemented and created our own TAT detection method, which we call ClassTAT, because it's based on clustering methods. And this method consists of the following step. First, we are starting from the single pixel on the diagonal to be a separate TAT. Then we are using bottom-up clustering to create more coarse TAT split. And then because merging TATs that are small in size usually results in very imprecise TATs, especially at the borders, we are doing clustering only to get a little more coarse TAT split, and which is still very fine compared to the final TATs. So as the first step, we are refining the obtained small TATs by adjusting the borders. And 4, we are again using bottom-up clustering on refined small TATs to obtain proper TATs. In both clusterings, we allow to merge only adjacent TATs, and we develop a custom distance metric that use 4 adjacent TATs to do this. We can threshold the second clustering on an arbitrary point, which results in the ability to obtain subTATs at different levels. Okay, next contribution, we evaluate and compare results for all 4 methods and several set types, and analyze CTCF binding size occurrences on TAT borders. And unfortunately, because of 3 slides and 3 minutes limit, we won't be able to show all of our preliminary results. So we ran our methods on 3 cell types, GM12878, Quebec, and HMEC, and did an initial quantitative and qualitative analysis of detected TATs. Some methods are much faster than others, for example, TOPBON and our ClassTAT. Some can detect subTATs, some not. For example, Arrowhead TAT3 and ClassTAT can. Some can produce only contiguous TATs, and many differences in quality of TATs. As for CTCF binding size, we took experimental data of CTCF binding size. We ran search of complementary sequences to CTCF binding size using consensus motif in both directions. And we see that sometimes good TATs have higher density of CTCF binding size, but we didn't check yet if it has any statistical significance. We met only one technical problem, which we resolved without any problems. So some methods, that is Arrowhead and TAT3, requires much more memory than we have available, and tremendous amount of computing time. So to tackle this problem, we are splitting the entire heat map on many square sub-heat maps along the diagonal. Every 2 adjacent heat map have an overlapping region. We are calculating TATs for every region independently, and then we are merging TATs from those regions, removing duplicates in the overlapping parts. Thank you for your attention.
Thank you very much. Do we have questions?
So maybe
I have a
I'll
question.
Oh,
sorry.
sure.
No, go ahead.
Okay. If in cases where you have overlapping TATs, like when you have to split the map and then do the TAT calling on various sides of it, do you always have agreement, or do you frequently find disagreements, and what do you do then?
Usually we have agreements, but what I essentially do, I'm taking. Okay, I'm basically merging TATs only if their IOU, intersection over union, is high enough. And if it's not, we just have 2 TATs. That's it.
Okay, thanks.
Okay, maybe I have a quick question. Did you see that the algorithms take different times of execution? Could you tell some word about which is more slow, faster, something like that?
Okay, so TOPDOM is very fast. Reading data takes more time than the algorithm. our method ClassStat is also similarly fast to TopDOM. Arrowhead is very, very slow, and especially in the paper they use 5K resolution or taken. So this can take like many days, maybe even weeks. And TAT3 is similar, maybe even smaller than Arrowhead, but in paper they use 100K. But even on 100K, it's very significant. Probably also more than 1 day on one core on chromosome 1, for example.
Okay, maybe we move to the next talk, last talk actually, no? Team 2 of Sorbonne University.
Okay, hello. Can you hear me?
Yep.
Okay, so I'm gonna start sharing. Yeah, okay, TCS. Okay, is it working?
Yes.
Okay,
Yes.
so hi everyone. So we are the second team of Sorbonne University working on the TAT problem. So our approach is to use the TopDOM algorithm and to then refine it using CTCF binding data. So I'm going to first talk about the TopDOM, the work on TopDOM that we did. So the TopDOM algorithm measures a signal along the diagonal of a contact map using a window. And so the first thing we had to do was to find an appropriate size for this window. After implementing TopDOM from scratch, we did some testing on one particular chromosome. And we determined, according to the literature, that a smaller window of, for instance, 5 bins in our case, yielded the results that fitted the best with our comparisons. We immediately witnessed a shortcoming of our approach for the moment that we have not solved yet. And it is that for the moment, regardless of the size of the window, as we can see here, we have some problems because the tabs we find are a bit too big compared to the arrowhead that we are supposed to match. Okay, so now Rasha is going to talk about CTCF manual.
Yeah. So as Duncan said, mainly the approach was also to look at specifically the CTCF binding sites. And the data we used was utilizing the ChIP-seq data, which actually does the job of kind of retrieving the reads themselves, so we wouldn't have to look at the whole genome. And after that, we've gotten the boundaries and the reads, but then they were too large. And so we've tried to kind of zoom in on the CTCF binding sites. And so with these two steps, with kind of getting only the domains that contain the CTCF at the boundaries and fine-tuning the TopDOM algorithms, is how we've approached this. So now Sian's gonna take on the next step.
So, as it was said
There you
before,
go.
we used the TopDOM with a Windows of 5. We wanted to compare our results with arrowhead ones, and here is a result on chromosome 12. Sorry. So the above one represents the results of TopDOMs, and the other one is arrowhead. So TADs are in blue, and the edges are in red. The edges is what we define as the bin directly adjacent to the TADs. And in yellow, we added CTCF binding sites. So what we can see first is that the CTCF binding sites are on the TADs as well, and not only on the boundaries. And also we see Sorry, that you have read past 3 minutes. Okay. So conclude, please. Yes. So one of the limits is that we are not sure of the relevance of our methods because, as you can see on the density diagram, there are
we do not observe more CTCF binding site at edges than inside or outside TADs. So thanks for your attention.
Thank you very much. Other questions?
Yes, maybe talk about the challenge that you have, the problems.
Okay, so the first one, as I said, was that when we look at the results we have given by TopDOM, the TADs that we find are significantly larger than the ones in the Arrowhead data that was provided for us and that we have to match as best as good as possible. So that is the first problem we're having at the moment. And then there's the problem of, so we did the work on CTCF binding sites, and we have some, we still do have some trouble understanding the relevance of our results, since we apparently don't find the significant enrichment of CTCF around that.
And could that be linked to the differences in resolution? I think another team mentioned the fact that it was not so easy to match these kind of data with the resolution of the Hi-C metrics, no?
Okay, I don't know about this.
Yeah, it could be actually, yeah.
Okay, so thank you very much, everybody. We are on time. That's very good. So right now what's going to happen is that starting from today, we're going to just open the repositories, and everybody's going to have access to everybody's repo. And so we're going to define the pairings. So I'm going to share my screen again, just to show you. Is that okay? Okay, so this is the pairing we propose. So the idea is that there are not so many possibilities, because in a pair you should be two teams from two different universities and addressing the same challenge. So we changed the initial idea we had of defining a combined challenge. So now your task within the pair will be to assess the results of the other team. So this implies defining metrics, which you already did to evaluate your preliminary results, and having some proposing some quantitative assessment of the results, possibly qualitative, and discussing about these results. So there is one, we cannot make just pairs, so the last group will be of 3 teams. So meaning that, okay, maybe you have to evaluate both, or it's not to add extra work for you, but well, you will see how you can arrange yourself. So is that okay for everybody, this pairing? So you will have to exchange between you, yeah?
One suggestion, couldn't we just like the Warsaw TED team pair with the Heidelberg TED team, and Heidelberg with Sorbonne, and Sorbonne with Warsaw, so like do a full circle that everyone evaluates one team?
A full circle, what do you mean? You would like one group with all the TEDs?
No, Warsaw evaluates the Heidelberg TEDs, Heidelberg evaluates the Sorbonne TEDs, and Sorbonne evaluates
yes,
the
okay,
Warsaw
okay.
TEDs.
For the three, yes, you can do this. Yeah. Yes. It's doable. That's a good idea.
I don't have anything against this pairing. What I would suggest maybe is that we could agree on some kind of a deadline for freezing the results, because I mean, several teams mentioned that they want to still, I mean, either continue to produce the results or even work on the methods.
Mm-hmm.
So I assume that in many cases we don't actually have the results as of yet, but it would be quite important
Yeah,
that
yeah.
we have a date at which we actually expect people to have something to evaluate for the other team.
Yes, it's a good point. So if we think in terms of retro planning, so the final meeting is going to be on the 25th of January. Everything should be ready like 10 or like 10 days before. So it would be great if if we freeze the results as soon as possible. If you
I don't
have
know,
the
at the
result,
end
like,
of the, I mean, reasonably at the end of, like, I assume everybody has something to give to the other
Yeah.
team as of now, but end of the calendar year?
Yes, yes.
Is it like maybe the
sounds
students
okay.
should speak up what they think? But I think agreeing here on some kind of a date is important. I don't have a preference, but I mean, maybe the students should speak.
Yes, what do you think? What do the students think?
Yeah, I think it would be helpful if we could maybe work on the results for a few more days, week, 2, I don't know. Like yeah, probably the end of the calendar year is pretty good. If 10 days will be enough to evaluate the results, which it should be probably.
For us also, it's important that our cluster will be down over the weekend and the start of the next week. Like they're doing some updates, so we actually don't have access until to it until next week, Wednesday, I think.
Mm-hmm. You mean for Christmas?
Yeah.
Yeah. So.
But maybe, like you mentioned, Bartek, probably most of the teams have some preliminary results. So actually, I think what would be good is to already share the preliminary results so that the other team can kind of, maybe already run some metrics and some evaluation, with the understanding that it's not the final result, but at least you can already write your script to evaluate, and then once you get the final results, it would be kind of easier to generate the evaluation, right?
Yeah, and can I add, as for code, like we could, for example, create a branch on the repositories where any further updates get uploaded and then just do a merge request so that the teams that are checking it actually can see what has changed in between the versions.
Yes, if you can. Well, it's also part of the evaluation if you can update the results you give in an automatic way or efficient way, let's say. Well, maybe we can push to the 5th of January, no? Because still, if it's the 5th, then until the 15th, it's still 10 days, and then 10 days for the final run.
Yeah, that's what I was just going to say, that the actual, I think in the document, the actual date is the 15th of January, like when we expect
Yeah.
because you mentioned that, yeah, so yeah, it could be later, but I think that the students should really think hard, because you're on both ends of this deadline, because you don't want it too late, because you will have no time to evaluate your colleagues' work, but you don't want it too early, because then you're shortening your own time to produce. So I think it's the best time for you now to discuss when exactly is the optimal date.
Create a poll. Do we create a poll? We can create a document. But it's true that you can start testing the measures and the evaluation metrics already on some preliminary data. So
yes, absolutely. That's what I suggested from the beginning. It's just that you will in the end want to write the final evaluation of the final results in the final report.
Yeah.
So you need some time for that, and I don't know what's the feeling among the students about that.
Okay, so we can create a poll. There's no problem, and then we can just put 2 dates, like 31st or 5, maybe. But it's good that you set yourself some deadlines, some fixed deadlines. Okay. Okay, great. So there is already a poll. So you just need to vote now in the chat. Good. So maybe next topic is the final meeting day. Okay, so we have 4 speakers. So these are the jury members. By the way, do we have 4 or 5? No, I think I'm okay. I hope I haven't forgotten anybody. I don't think so. So the meeting day should be like this, should be the program. It will start around 9, let's say, with an introduction, and the morning will be dedicated to the presentation of the project. So we have 9 teams, I think. So each team should present for 20 minutes, including the questions. So you should aim for 15 minutes and 5 minutes of questions. By the way, I want to say that some of you today showed some pictures of the different members of your team. This is very good. I think you should do it. Everybody should do it on the last day, because this is going to be virtual. So essentially, people are not really going to see you. I mean, even if you talk, it's not. So it would be good at least to have just the faces of everybody on one slide to kind of, really show the team. So we'll have a short coffee break, which will be lonely, of course, but well, that's the setup. And in the presentation, we'll have the seminars from the jury members. So each jury member will give a 30-minute seminar and then about 10 minutes for questions. So if it's 5, it's okay. So we have Julien Mozziconacci, which is at the Museum of Natural History in Paris, and Benoît Moindreau, University Paris Sud, Nicolas Servan, Institut Curie, and Alexandra Pekowska at the Nanki Institute. So I just put here some order, but this may change. The important point is that it's very important that you try to attend the whole day if you can, and also that you ask questions to the jury members. So in principle, we shouldn't ask any questions. That's really should be, something that is animated by you. So that's the whole idea of the day. In the morning, you present, you're evaluated by your scientific peers, which are the jury members. And in the afternoon, it's the reverse. So they present and you ask them questions. So if you can, in advance, if you need preparation, maybe in advance, you can take a look at what they do. And if you're very keen on asking questions, then you don't need preparation. That's great. But it could be really nice that you actively participate in the afternoon. Okay.
Every question will lead to a bonus point.
The questions lead to bonus points?
Yes.
Yeah. But usually in the other occasions it works quite well. So we had this kind of dynamical discussion, and the jury members were very happy. So I hope we can still do this, even if it's virtual. It's a bit different, but so is that okay? Do you have questions about this? How many votes?
How will the jury then convene to evaluate, or how will that be on this day, or?
Yes. So the jury members are gonna, so for the final, what you have to handle, so you have to handle your code and written reports. So it's gonna be 1 2-page digest explaining briefly your strategy and your main results with a figure, with a picture, and a full report of maximum 10 pages. So I will provide you with some template in the next days. just to be sure that we don't have formats that go a bit wild. So the jury members will have access to the codes and also to the reports. So they will probably read at least the digest, and depending on if they are interested or not, the reports as well. So they will be able to judge based on the report, on what they read, and also on the presentations. And so we will ask them some kind of grades on the day, or if they cannot on this day, it can take a bit more days. It's not really a problem. They exchange, and then we make a consensus of their grades, and this is going to be a part of the final grade.
A question maybe not directly related. So the presentations from today, so we agreed that they're not part of the evaluation, but I think it would be nice if they were made available in some kind of a PDF form by the teams. I don't know, on the GitHub or somehow. I mean, even for each other of the pair, like can we?
Yeah, sure. That's a good idea. Put them on the sharing repo, no problem. So I don't think the students can directly write there, so you can just.
But if we're making the repositories public, then they can just put this on their own repo.
Yes, they can do that, and then I can still copy in the main. Yeah, but yeah, okay, yeah, it's a good point. It would also be good to get some feedback on today's presentations. So me, generally, I thought they were very good, honestly. So one thing that was that should be added in the final presentation is some presentation of the subjects, let's say. So it's a bit tricky because everybody who is doing the same task is gonna kind of present the same thing, but still it's good to put it in context. Otherwise, I don't know if other want to say specific stuff. So if you put your slides on indeed on your personal repo, then we can also maybe ask you questions, because we didn't have much time to ask many questions. So maybe we can ask questions directly through the GitHub conversation issues. That can be good too. So I think I had other questions that I could ask by writing. Okay. How many votes should we expect? You mean for the date?
Yeah, for the date. Because like at how many votes should I close the poll? I expect everyone to be not to be an asshole and vote just once.
Yeah, but it's just to have an idea. I mean, if some tendency is really strong, it's easy to decide, no?
I mean, it's 60 to 40 now, so
16 to 40, no. How many?
60% to 40% in favor of the fifth.
But how many participants?
Votes, 27 people voted.
27, okay. So but there is still time.
It's probably enough.
It's actually 29 people now.
Okay.
We can wait a bit more.
So maybe we just say it's gonna be the fifth because it looks like it's winning out. And or if someone hasn't voted yet, just vote.
Yes, those who don't vote, they don't get to choose.
Yeah, that's
So
democracy.
If you have an opinion, just vote.
Yeah. Okay, now it's even more in favor of the fifth. Okay, I think so. The fifth, it is.
Okay, so that was expected, no? The most remote deadline.
Yeah, I guess.
Okay, so that's the deadline for the final results. Not evaluation results, but final prediction results.
And so the report and the digest are due for the 15th, right?
Exactly.
Okay, thanks.
Deadline for final codes plus reports should be the 15th. So this, it gives some time to the members to read stuff and also for you to prepare the presentation.
I think it would be important that right now the paired teams kind of agree on how they want to share and what type of format they want to share the results, right? Just to make sure that they can already start writing scripts to evaluate and can quickly run on the updated results once they are ready. But maybe already now communicate and then kind of agree how you want to share and what format you want to share results.
Yeah, that's a good idea.
So are we expecting them to use the same evaluation metrics, or can every team kind of
In the end, I think they have some freedom because this is this is a real task. So I would say we don't have to have exactly the same metrics.
But within a pair.
Within a pair.
Do we? I mean, it would make sense for them to kind of evaluate their results in the pair, at least with the same metrics, no?
Yes. It's
yeah,
true.
I guess that's always good practice if you are comparing use the same metric for each of those.
Maybe they won't. Maybe they won't agree at all.
Just to make it sure for those for whom it is not obvious, we are not expecting you to show that your method is better than the other. That is not part of the evaluation. But we expect you to. I mean, you will absolutely score better if for whatever reason it turns out that you are outperformed by your partners in this, then it's great. You can use the second leg sort of to show your creativity and skill in kind of really emphasizing how much you were outperformed, so to speak. So this is I think the spirit that at least how I understand it, not kind of to try and bend the methodology so that you look better in the second part. I guess that it's part of the sentiment that Carl was mentioning here.
Yeah, absolutely.
Maybe could I have a suggestion? Maybe it would be good for like both teams to agree on the same methodology, because then they can like cross-check. I don't know, maybe not, but
yeah, I think it would make things easier if within a pair they use kind of the same evaluation metrics, which means that they have to kind of agree and discuss what they believe would be the best metrics and the best evaluation strategy, right? I think that's, like you said, Bartek, it's part of the task to do this.
Yeah, it's good if you can exchange more than just giving your results, handing your results,
Yeah, absolutely. So I think so maybe here I just put again my 2 cents into this. So I do think that it's absolutely, like, if you want to make the evaluation good and you have the ability to communicate with the other team, which you do, it's absolutely great if you agree on some part of the benchmarking to kind of have a common ground. And then you can always also do some things on your own to kind of, because I mean, we don't want to hear the same report twice in pairs, right, of the evaluation. Like it would be, you will both have 20 minutes to discuss, and you can also, I mean, I expect, like, maybe do not misunderstand me in a way where I said something about outperforming the other team in any way. It's about kind of having your own approach to the analysis as well. Like that's encouraged, I think, to kind of try different things at evaluating and sort of elucidating different aspects of the comparison, and this is great. But then there should be some common baseline of like of evaluating both against the ground, truth.
Okay.
Okay.
Should we write a report about the evaluation about the method? So the report is going to be about everything. Yes, I can. Yes, I will put the sharing. Yes, I would put the pairing. I can put it here also in the. So in the report here, you're supposed to put everything, meaning the presentation of your method, presentation of your results, and the assessment of the. So if you wish, the pairing with another team is kind of an excuse to make you really do some kind of rigorous evaluation and some thinking about the measures and the metrics. So this is what you should emphasize. Then if we share metrics, there will be a lot of things in common. Yes, so that's what Bartek was saying. I guess you should keep some way of analyzing the result that is yours as well. So you should agree, let's say, on the way you assess and on the results you obtain from the assessment. But I mean, if you have an idea for the measure, you're explaining this idea in the report, it's yours. You can keep this way of seeing things. In any case, for the presentation, the final presentation, you will present your method, your strategy, and not the strategy of the others, right? So that will be the assessment of the results. But it's true that it's good if it's not exactly the same thing that you tell about the assessment.
For me, the best way to answer that part is just that they know that they compare themselves to another algorithm, and so they can explain how they can improve their code to beat the comparison. So it's a game of, okay, maybe they are better, maybe we are better, but what can we improve? What is the feedback that we have from this comparison? And so this makes this, okay, you have the common metric, which will be maybe 10% of the report that will be a little bit common with the same part, but at the end, it will be more a discussion about what you do and what you keep in mind from this comparison.
Yeah, let's say the comparison is centered from your point of view, but you will agree on the assessment. Should we only introduce the method to evaluate each other and also include comparison results? In in the report you should include comparison results. Yeah, I mean it's when you present the results you can just have a quantitative assessment that includes the comparison with the others, because in any case you're going to assess your own results as well. So for the report, in any case, I will share some guidelines soon. So here I'm just gonna copy this. Can I put this in the chat or not? So I will put the slides of today just right now on the GitHub, so you will have access to the information and to the pairing. Okay, maybe that's better. What's the report address? There a page limit? Yes, there is a page limit. It's 10 pages. So I will specify this. Maybe I add a slide about the specification for the report. I didn't have time to put them. So it's 2-page digest and then 10 pages for the report, single column. Okay, I just put an image for the pairing on the Discord. Is there something else? So in today's schedule, we also had Q&A session, and then we're good. So, okay, I will complete the slides just to write again the deadlines that we mentioned, the result of the vote, and some information about the reports. And I will put it on the GitHub. And I will open the permissions tonight or this weekend. Okay, so everybody's happy? So if there are no more questions, maybe we can stop here. Is that okay? So try to, very happy, that's great. So try to already exchange with your partner in the team, in the pair. And as Carl said, to arrange on the, at least on the format of the data, of the output data, what you're gonna exchange. So good afternoon, everyone. Bye-bye.
Yeah, thanks a lot. Thanks.
Bye.
Bye-bye.
Thanks.
Bye.
Bye bye. Thank you.